Hi, I'm Bhupesh, and in this video, I will be explaining how to draw the or sketch the particular root locus. And in order to sketch any root locus, we will be requiring a transfer function. So, transfer function we already know it is the ratio of Laplace transform of output to that of the input. So, when we take roots for the numerator, it is called zeros, and when we take roots for the denominator, it is called poles. So first, there are different steps in the root locus. We'll see each and every step. So the first step tells that we have to determine the poles and zeros. So as I told, the denominator part, when equated to 0, or when we find the roots for the denominator, we get the zeros. So I'm taking the denominator of the transfer function and equating it to 0. So one root is 0, and the other root, with the help of formula minus b plus or minus root over b square minus 4ac divided by 2a, gives us the solution minus 2 plus or minus 3j. So when we split this, we get two roots, minus 2 plus 3j and minus 2 minus 3j. Here the imaginary part is represented as j, root over minus 1 is j. Generally we represent it as I, but here I have taken it as j. And the second step is to find the particular root locus on the real axis, or we have to draw the particular root locus branch. So actually there is only one pole on the real axis, because one pole is the poles are represented as a cross mark, and there is no zeros because the numerator has no s variables. So I have represented the poles as cross marked, cross ink, red color, pink color ink, and one pole is 0 and the other two poles are minus 2 plus 3j and minus 2 minus 3j. So on the total real axis there exists only one pole, that is on the 0 margin, the center point. So we consider a particular line or a thing as a root locus branch only when by taking some trials. For example, if we take minus 2, when we look at the right hand side, only one pole exists. So whenever there exists odd number of poles, then we say that there exists a root locus branch. So 0 to minus 2, there exists a root locus branch. Similarly, when we take each and every point till infinity on the real axis, we will get only one pole on the right hand side. So the total negative real axis is called as the root locus branch. Actually, this is an S-plane where x-axis is represented as the real axis and y-axis is represented as imaginary axis, where real symbol is represented as sigma and imaginary symbol is represented as j omega, and the total thing is called S-plane. So after representing these three poles on the graph, we are going to the next step, that is step 3, to determine the angle of the asymptote. So we have to determine the angle of asymptote. So here the angle of asymptote actually has a formula, 180 plus or minus 180 into 2q plus 1 divided by n minus m, where n is the number of poles, m is number of zeros, finite zeros specifically, where the number of zeros is 0, therefore we put m is equal to 0 and n is equal to 3, and q is nothing but n minus m. So where 3 minus 0 is 3, so we have q as 3. So it means that we have to substitute q value each and every time. That is, for 0 q value we will be getting an angle, for 1 q value we will be getting an angle, so 3 will be getting an angle. So if we get the angle again and again, the same angle gets repeated, then we can stop at that particular q value. For example, when we put 0, we get the angle as 60, and when we put 1, we get it as 180, and when we put 2, we get it as 300. So when you take tan 300 or tan 60, the answer is 1.73 or minus 1.73. So it will be varying between the signs. So that's the reason why instead of 300, it is taken as 60. So since we have 60 here, we take the particular asymptote angle as 60. So before drawing this asymptote line, we have to find the centroid in order to because the asymptote line should start from a point, so we find the centroid point. So the centroid also has a formula, sum of poles minus sum of zeros divided by n minus m, where we already have calculated the sum of poles, that is taking roots for the denominator. One is 0 and the other one is minus 2 plus 3j, and minus 2 minus 3j is the third pole, and 0 is 0, therefore we put it as 0 and we get it as minus 1.33. So here we have taken minus 1.33 as a point, and we have calculated the asymptote angle to be as 60 degrees. Therefore we take plus 60 and draw an infinite line, and we take minus 60 and draw an infinite line. So we have completed step 3, and we are moving on to the next step, that is to find the breaking and breakaway points. We actually find this breaking and breakaway points in order to make sure that the root locus is not continuous in this branch. Here it is continuous, but in some problems it won't be continuously ranging from 0 to minus infinity. There will be some breakaway in between lines. So in order to determine that, we'll be calculating the breaking and breakaway points. So for that, we consider the transfer function to be as a closed loop unity feedback system. So when we take closed loop, then we can solve it by using g divided by 1 plus gh, that is block diagram reduction rule technique. With the help of that formula, we have solved it and taken the characteristic equation, and here we keep k on one side and we take the rest of the variables to the other side. So we are differentiating the k with respect to s, so we get this equation and equating it to 0, and we find the value of s with the help of same formula. So minus 1.33 plus or minus 1.6s. So we substitute this value in the k and find the value of k. If the k value, by substituting this s value in k, we'll get a certain value for k. If the k value is positive and real, then only it means that there exists a breakaway or breakaway and breaking points. If there exists no real positive or real value, if there exists instead of that, the other value is nothing but the imaginary value. So here there exists an imaginary value because j is root over minus 1. When we take here it is represented as s cube, so minus 1.33 plus or minus, we take it as plus 1.6 j whole power cube. Either you take it as plus or you take it as minus, it is j cube, which is nothing but minus j. So root over minus 1 to the whole power 2 is nothing but minus 1, and again that one multiplied by j is nothing but cube, so minus j is the value. So this is not positive and real. We can conclude from this, and we can say that it is imaginary, therefore there exists no breaking and breakaway points. So with this we stop this step 4 and we go to the step 5. So in step 5 you have to calculate the angle of departure, because here there are two poles lying in here. For that we have to calculate the angle of departure so that it has certain root locus branch. We have to draw the root locus branch. Here one branch is this 0 to minus infinity, the other two branches are to be found out. So theta 1 is equal to 180 degree minus tan inverse of 3 by 2. So how I got this tan inverse of 3 by 2 means, this is the root locus, the calculation of angle, that is angle of departure. So here when we have theta 2 at this particular stage, we have the formula 180 degree minus tan inverse of a by c. A is this distance and c is this distance. So this angle is taken, and this theta 4, theta 3, theta 1 is not there in our root locus problem. This type of there exists no sort of angles, therefore we leave it. But whereas we have theta 3, which is nothing but 180 minus tan inverse of a by c, and sorry, that is theta 2, and theta 3 is 90 degree. So what we do is we have to calculate both angle of departure and angle of arrival. So here we are calculating only angle of departure, and angle of departure is nothing but 180 degree minus theta 1 plus theta 3 plus theta 5 plus theta 2 plus theta 4, where theta 2 exists, theta 4 does not exist, theta 1 does not exist, whereas theta 3 also theta 3 exists and theta 5 does not exist. So we take theta 3 here and we take theta 2 here. So with this we calculate the angle of departure. That is what is done here. So for pole P2 we have calculated the angle of departure to be as minus 33.3 minus 33.7. So similarly for angle of departure for pole 3, that is this is P2 and this is P3. So this is minus 33.36 means we have to draw it along the negative axis. So the angle will be coming along downward direction, whereas here it is said to be positive because same values are going to be substituted, theta 1 and theta 3 on the negative direction also, so we will be getting the reverse value of the angle. So that's the very reason why we are taking it as 33.7 degrees. So finally we have to calculate the crossing point on imaginary axis. So how do we calculate this? First we take the characteristic equation and put actually we in order to calculate the roots for the characteristic equation, we can either do it by root array criterion or Lim's trial and error method, that is the long division method, or we can also use s is equal to j omega and calculate the values. So I am taking s is equal to j omega and obtaining a certain equation where I am equating real parts to 0, where I get the omega is equal to plus or minus 3.6, and when I am equating the imaginary parts to 0, I get the gain value k as 52. So from this I can easily draw the particular root locus plot. So this is the root locus graph that I have completely drawn, where, one second. So this is the margin, this is one pole, this is pole 2, this is pole 3, and this is the angle of departure for pole 2, and this is the angle of departure for pole 3, and we have calculated the real part values and imaginary part values. So the real part value stated that it is said to be passing through minus 1.366j, right? So here is the value, plus or minus 3.6j. So P2, that is pole P2, crosses at 3.6j and goes till infinity by making sure that it is parallel to the asymptote line that is drawn here. The dotted line is called asymptote line. And similarly for pole P3, it is also said to be intersecting at minus 3.6j, and it is said to go parallelly till infinity. Till infinity at parallel to the asymptote line. So here we have calculated the k value and also the respective angle of departure values. So from this we can say that 0 to minus infinity is one root locus branch, and this pole P2 we have taken angle of departure, and then we have intersected at 3.6j by calculating the angle by taking the real roots equal to 0 and taking it to infinity. So this is another root locus branch, and this is another root locus branch. So 3 root locus branches are sketched. So here the number of poles is greater than 0. So from that we can conclude that these branch terminates at infinity. The root locus branch terminates at infinity because number of poles is greater than 0. So this is how we sketch the root locus. Here's where I'm going to leave. Thank you.